Back in the 1800s, there were a lot of experiments done on gases. And what they found is that all of the properties are related to one another. And that relationship comes very close to what we call the ideal gas law. Now, that's kind of a funny name. It's not an ideal law, but rather it's a law about ideal gases. So we need to look at the relationship, but also consider what an ideal gas is. Gases have been studied quantitatively for a long time. Back in the 1600s, Robert Boyle showed that the pressure of a gas in a closed system was inversely proportional to its volume. In other words, if the volume went up, the pressure went down. In the 1700s and early 1800s, several scientists showed that the volume of a gas in a closed but flexible container was directly proportional to its temperature. In other words, if the temperature went up, the volume went up. If the container was inflexible, then an increase in the temperature resulted in an increase in the pressure. Temperature and pressure were directly proportional. Finally, in the 1800s, it was shown that the volume of a gas in a flexible container was proportional to the amount of gas present. All of these ideas were put together in the mid-1800s into what we now know as the ideal gas law, PV equals nRT. This equation contains the four measurable quantities of a gas. In the equation, R is a constant, called the ideal gas constant. We are talking about the ideal gas law, but what is an ideal gas? There are three things that make a gas ideal. First, the volume of the gas particles, atoms or molecules, is negligible compared to the volume of their container. Next, the gas particles move randomly throughout the container. Finally, there is no interaction between molecules. All collisions between two molecules or between a molecule and the container walls are elastic. While the second condition, random motion, generally is obeyed by most gas samples, the first and third conditions are generally not obeyed by real gases. When gases are compressed, they can take up a significant portion of their container, so the volume in which they have to move around is actually smaller than the container. Also, the attraction between molecules can change the speed at which the molecules strike the walls of their container, affecting the pressure they exert. While there are mathematical ways to take these effects into account, we won't pursue those in this section of CH 101.